So hello everyone. So in this lecture I will discuss about the convergence of a sequence which is bounded with some additional property. That property is called monotonicity. So in the previous lecture we raised a question. We posed a question like, when a bounded plus what property implies convergence. Okay, so this property is called monotone. Okay, so we define monotone sequence. Okay, so a sequence n is called increasing or monotone. Increasing if n is less than equal to n plus 1 for all this. Strictly monotone increasing if n is strictly less than n plus 1 for every n belongs to n. Okay? Similar way, we say that this sequence is monotonically decreasing. Monotone decreasing if for all chain and if for every n belongs to n. Okay, sequences, so note that are either monotone increasing or decreasing are called monotone sequence, right? So it can be strictly monotone increasing or strictly monotone decreasing. That are also called monotone sequence. Okay, so strictly, if this inequality is strict and just increasing if less than equal to, similarly decreasing if this is reversed, and strictly monotone decreasing if this is strictly bigger than. Okay, example, n equals to n is strictly monotone increasing, right? Because n plus, since n plus 1 equal to n plus 1, so is always bigger than n, so n is for every n and n, right? N equals to 1 by n is strictly monotonically decreasing, since n plus 1 equal to 1 by n plus 1 less than 1 by n, so n for every n belongs to n. Okay, strictly monotonically decreasing. Third one is, you take n equals to 1 for every n belongs to n. What is n plus 1 is 1 for every n belongs to n. Right, so n plus 1 is n for every n belongs to n. So this is both monotonically increasing and monotonically decreasing. Okay, yes. So now we take another example. For example, this one, minus 1 to the power n. What is n plus 1? N to the power n plus 1, right? Which is minus of minus 1 to the power n right, n belongs to n. So for example, I will prove that this is not monotonically increasing nor monotonically decreasing. Because what is a1 minus 1? What is a2? a2 is 1, a3 is minus 1, a4 is 1. So if it is monotonically decreasing, then a4 should be bigger than a3, right? If an is monotonically increasing, then this, right? But a4 is 1, sorry, a3 should be, if this is monotonically increasing, then a3 should be bigger than this, but a3 is minus 1, a2 is 1, right? So not monotonically. If an is monotonically decreasing, then a4 should be less than a3, right? I mean bigger than equal to this, but a4 is 1, a3 is minus 1, right? Yes, right? This is not true, right? So the sequence an is neither monotonically increasing nor monotonically decreasing. Okay, now we'll try to answer that question. When the question was bounded plus what implies convergence, right? So we'll answer this question. We'll prove that bounded plus monotone sequence implies convergence. So this is the answer. Okay, how? So write a theorem. So theorem 1. Let n is a bounded and monotone increasing sequence, then the least upper bound of this an, this set is the limit of the sequence as n goes to infinity. Okay, so what it is saying, suppose I have a sequence which is increasing, okay? It need not be strictly increasing, it can be it just has to be increasing like this, but it is bounded. Suppose it is coming from like this, it is bounded, right? So suppose it's saying that it's going to the least upper bound or the supremum of n such that n belongs to n, this set. Okay, supremum of this set. This is the limit and this is my n. Okay, monotone increasing plus bounded. So if you are bounded, then monotonically increasing implies that this is the limit. And since it's bounded, okay, so the supremum is a finite quantity, it's some real number, right? By the supremum principle, right? Every bounded subset of R has a supremum in R. If this set is non-empty, here this set is non-empty, right? This set n is such that n belongs to n. So how do we prove it? So let supremum of an such that n belongs to n, an is equals to n. And then are given epsilon bigger than 0 such that a not. Okay, since n is monotonically increasing, we have a not less than equal to n equal to m for all n bigger than equal to n not, right? Since this is monotonically increasing, so a n not, yeah, right? Because n bigger than equal to n not implies n bigger than equal to n not because due to monotonically increasing, and since capital M is the supremum, each n is less than equal to m in particular for all this n, right? Now, so what do we get? If we start from 1, this is my 1, this is my 2, so by 1 and 2 for every n bigger than equal to n not, m minus epsilon is less than equal to n not by 1, by 2 this is less than equal to m, this is less than equal to m, but m is less than m plus epsilon, right? So what we get is that is that limit n goes to infinity n is m, right? And m is nothing but supremum of n belongs to n, right? Yes. So similar fact can be proved for a decreasing sequence. If the sequence is decreasing, it will go to the greatest lower bound. So suppose I am starting my b1 from here, it goes like this, it will go to the, if it is bounded again, then it will go to the greatest lower bound. So I will write that statement without proof. The proof is similar. Okay, so this is my theorem 2. So let n be a bounded and monotonically decreasing sequence, then limit n goes to infinity n equal to infimum of n belongs to n. This is the greatest lower bound, right? This infimum is exist because bounded n is bounded means again I have some bound. Okay, this is the bound. It is monotonically decreasing. I mean, okay, no, sorry. You can think like this. Yeah, the picture should be like this. So suppose the picture is like this, the value is like this, and this is your, yeah. Suppose this is non-negative, for example, it is a decreasing sequence, it goes to the greatest lower bound, okay? This is my n decreasing, okay? It may be that it is taking same value at some portion, but it is going there, okay? Yes. So, okay, so we'll apply these results to solve some problems. Okay. So actually you see, like, you need, it is enough to assume that n is bounded above here, right? Because it's monotonically increasing, right? So monotonically increasing, so you have some first element, all the other elements are like this, so automatically you'll get this boundedness. Same thing, it is enough to assume bounded below here because of monotonically decreasing property, okay? It will be automatically again like bounded because it will start from here, and if it is bounded below, then it is both upper and lower bound, okay? So now application. What is application? So find limit n goes to infinity n where a1 equals to square root of 2 and n is given by 2 plus n minus 1 where n is strictly bigger than 1, okay? So in first claim that 0 less than equal to n less than equal to 2 for every n belongs to n, right? Okay, so observe that by definition n is bigger than equal to 0 for every n belongs to n, right? Because 2 plus n minus 1, so each n is like 2 plus, this is non-negative. Okay, by induction, so for n equals to 1 we have a1 is equal to root 2, which is less than 2, right? Let ak is less than 2 for some natural number k. We claim ak plus 1 is less than 2. What is ak plus 1 by definition? 2 plus ak, but this is less than 2 plus 2, right? ak is less than 2, so this is 2, right? ak is less than 2, and so the square root function is a positive number, so it's like x to the power half function, right? It's by it's an increasing function, so ak plus 1 is less than 2, so by induction we can say that this is less than 2 for every n belongs to n, and this is less than equal to 2, right? And suppose this is less than equal to, right? Less than equal to, less than equal to, yes, less than equal to. So 0 less than n less than equal to 2 for every n belongs to n. Okay, now we claim, so we have a bounded sequence, right? Now we try to check that n is also increasing, n is monotonically increasing. Okay, so to prove this we will like, I mean, this is not very difficult to check. Okay, you can just I mean, basically you have to prove that this is bigger than equal to this for every natural number n. Okay. So what we'll do is that you find your an plus 1 square minus n square. This is by definition 2 plus n minus 1 minus n square. Another by 2 plus n minus 1 minus 2 minus, sorry, this is n minus 1 square. So sorry, this, hey, something is missing. Wait, n minus 2 minus n 2 plus n minus 2 minus n minus 1 n minus n minus 1, right? Like this, yes. So that says that n plus n minus n and n plus 1 plus n is equal to n minus n minus 1, right? Observe that this is always non-negative, so they have the same sign. So if n is bigger than equal to n minus 1, then n plus 1 is bigger than equal to n, right? And vice versa. And vice versa means, or if n is less than equal to n minus 1, then n plus 1 is less than equal to n. And these both are true for every natural number n, right? Yes. But observe that we observe that A2 is bigger than or equal to A1, since what is A2? 2 plus this root 2, right? And A1 is root 2, which is always bigger than root 2, which is A1, right? A2 is bigger than A1, that implies A3 bigger than A2, right? So this cannot happen, so the only possibility is this, right? Yes. So n plus 1 is bigger than or equal to n for every n belongs to n. So now we have a bounded and monotonically decreasing. This is bounded, this is monotonically increasing function. So by theorem 1, limit n goes to infinity, n equal to supremum of n belongs to n, right? So let's say that is some L, and we have that n equal to square root of 2 plus n minus 1. So now that implies you can take the limit on both sides, which is 2 plus n minus 1 power half as n goes to infinity. This is a non-negative sequence, limit can be put inside, so that is basically 2 plus limit or half. So you'll get like L square equal to 2 plus L, and that gives L square minus L minus 2 is equal to 0. That implies like L equals to minus B plus minus B square minus 4 into C divided by 2 A 1 plus 3 divided by 2. So equals to 2 1 minus 3 minus 1. So but since each n is greater than or equal to 0, so limit n, which is n is bigger than or equal to 0, so L equals to 2, right? So the limit is 2. Okay, this is the first application, right? The second one is find limit n goes to infinity an or a1 equals to 8 by 2. Okay, so we observe that n plus 1 minus n is n by 2 plus 2 minus n, which is 2 minus n by 2. Right? So which is actually 4 minus n divided by 2. Am I correct? Yes. So observe that a1, so put a 2, let's say 2 minus a1 will be 4 minus a1 by 2, which is 4 minus 8 by 2, which is negative, right? It is less than 1, right? What about a3 minus a2, right? 4 minus a2 by 2, but what is a2? 2 plus 2 equal to 4 plus 2, which is 6. 4 minus 6, I don't negative. A3 is less than 2. What is what is So a1 is bigger than, so this is, so my question is each an bigger than 4? So let ak is bigger than 4. So what about ak plus 1, right? ak by 2 plus 2, this is bigger than 4 by 2 plus 2 equal to 4. So by induction n is bigger than 4 for all n belongs to n, right? So since this is bigger than 4, so by this formula this is always less than 0, so I get that this is less than n, and this is true for every n belongs to n. So the sequence is monotonically decreasing, right? Monotonically decreasing, right? Yes. Now we observe that n is bigger than 0 for every n belongs to n. This is by definition, right? Because a2 will be bigger, a2 will be 1 by 2 plus 2 is positive. Similarly, each n is positive, so implies n is bounded below, and the sequence is monotonically decreasing, so n is bigger than 0, and each n is less than equal to a1, let's say, right? Yes. And n is less than equal to a1 for every n belongs to n, so n is bounded, so bounded and monotonically decreasing. So by theorem 2, limit of n goes to infinity n, we can do m is nothing but infimum of n belongs to n. Right, so I've given that n plus 1 equal to n by 2 plus 2 implies I can take limit, and this will be half of limit this plus 2 equals to m by 2 plus 2 implies m equals to m by 2 plus 2 implies m by 2 equals to 2, m equals to 4. So the limit is 4. Okay, this is another application. So at least in this lecture we learned that bounded plus monotone sequence, bounded and monotone sequence of real number is convergent. Okay, and also we found what is their limit. For monotonically increasing it is the supremum, for monotonically decreasing it is the infimum, and we solved two examples. We found two limits and applied these two results. Basically this theorem 2 and this theorem 1.